Alright, so these are the concepts that you should know for our test tomorrow on work and energy. So work is force times displacement in the direction of that displacement, which you can find with cosine of theta. And this is the main thing that we are focusing on. Work is basically the change in energy of a system, and this is going to be what most of the questions are about. Energy is related to work, and energy is just the capacity to do work. Also, because work is force times displacement, you'll see that in a graph of force and displacement, which you might also see change in x, the area under this equals the work. So he might give you a question where, like, this is, 3 by 2, and they'll say, 3 newtons over 2 meters, as displayed in the graph. You'll have to find what the work is. You can just multiply it to find the area under, which 3 times 2 would be 6. Now, for our sake, these are the only 3 types of energy that'll be in these problems, aside from lost energy, which can happen basically due to internal energy, which is just heat. So internal energy is heat, and this energy is lost when there's some sort of other force that loses energy. So this might be from friction or from air resistance, would be the most common that you see this from. And so that's what would cause you to lose energy in a problem. But for the most part, you will not lose energy, and it will be made up of these 3 things. So for instance, if at the start of a problem, you're on the top of a cliff, and then there's a spring attached to you, and then you fall partway off the cliff, and then the spring is still attached to you, and you also are moving downward, the way that you would find all of this out is because the energy at the beginning will always equal the energy at any other point, such as while you're falling, which also can be equals all these energies added together. Now, for these problems about energy, it's all going to be treated as systems, and there are 2 types of systems, open and closed. And so for the most part, we'll be dealing with closed systems because they're a little bit simpler to understand. But there will also be some open systems. And an open system is basically where there's some sort of outside force that is acting on the system. So for instance, if the closed system is just a ball rolling down a ramp, the open system might have the ball being pushed by something else. And the reason why this is an open system is because there's energy from outside the system acting upon it, and that's why there's a change of energy within the system, right? Because we know energy cannot be created or destroyed, so if it's added to a system, it comes from outside the system. It's not being created. Now, the next thing I would say you should know is energy graphs versus both the distance fallen, so this is for a falling object, versus the graph between energy and time. So obviously the total energy will always just stay the same, but most of the time these graphs will ask you about a certain type of energy, which might be, the gravitational potential energy or the kinetic energy. And so when it's the distance fallen, these graphs are linear. because as you fall, the energy is proportionate to that. However, the thing that you should note is that energy versus time will not be linear. It will be exponential, because, right, as we saw the equation for your velocity versus time, we know that is exponential, and the relationship between kinetic energy and velocity is also exponential. So this graph will be curved, not straight. Now, one thing that I think is interesting to think about for this, and you should understand conceptually, I don't know that this will show up, I don't know that it won't, but this is a problem imagining three springs, which are all somewhat stretched, right? And there's a mass connecting them in the middle. And they're along a wheel, like depicted like this. So imagine that each of these springs' natural state is just to be kind of small like that, right? But they're stretched out, connected to this, so they can't retract. There's a question in the workbook about this, and it asks, if you moved the mass to here, essentially stretching this spring, but lessening the length of these two, would you be increasing or decreasing the potential energy of the springs in this system? So there's two ways you can think about this, right? You could, because I think they gave you the numbers for all of this, you could figure out the potential energy using the potential energy of springs equaling 1/2 k x squared, where x is the displacement. But you could also think about the fact that this is a open system where you are the only thing acting on it, and you are doing work, right? You're moving this object, and your work is increasing the potential energy, right? Because when you do work on a system, you increase the energy in that system. And when you increase the energy, it has to go somewhere. The only case this would not be true is if you did negative work. So imagine a shopping cart rolling down a hill, you do work to stop it, right? You are decreasing the energy. So in this case, I guess it would be hard for you to immediately know whether or not you're doing work, positive work or negative work. It's hard to differentiate because you don't know which way they're going, right? Because this isn't moving anywhere. But since it isn't moving anywhere, you can say, okay, the displacement is this way, the direction we're going is this way, therefore it must be positive work if you're moving something from a standstill. Also, another way you can think about this is what would happen if you let go, right? If you let go of a little dot attached to three springs, it would go to the middle. So if you're stretching it away from the middle, you're increasing the potential energy, because the potential energy is the ability to do work, and when you let go, that ability will be turned into the motion of that dot going back to the middle. So you should know that you add up all of the different types of energy, which we only know 4. When you add these all up, you get the total energy in a system. The total energy will not change if it's a closed system, and if it's an open system, the total energy, which we'll say is, E2, will be equal to the initial energy plus the work done, right? That's for open systems. So either way, whether it's an open or closed system, you should be able to figure out the total energy, and then you can create a new equation to figure out whatever thing they're asking you for. So most of these problems, you'll start out with one situation, right? Guy on top of a cliff. You'll get another situation, and they're going to ask you something about this situation. Most of the time, the way that you do that is taking this situation, finding the total energy, then realizing that the energy of this situation equals the energy of this situation, then breaking down the energy in this situation into components, such as height and kinetic energy, and then from there you can find whatever one of these components you need, probably either height or velocity in this case, But if it's a spring, they might be asking you about the displacement of the spring, so on and so forth. Another thing that I saw that was a little bit tricky was the problem about the bungee jumper, who's basically jumping on a spring, where it asked you how far down will they go before they come back up. For that one, what you have to realize is that when they stop going down and start going up, their velocity will equal 0 for a moment, and that will be their lowest point. So jumping down with a spring, similarly to what we did earlier in the year with throwing a ball upward and then back downward, the extrema, the highest or lowest point, will be when the velocity equals 0. So work, in addition to equaling force times displacement, also can be defined as the change in kinetic energy. This can be useful for problems where force or displacement are not given to you, but velocity is. So you can use this formula, right? 1/2 mv squared, where this v is your current velocity, minus 1/2 mv squared, where the second v is the initial velocity, indicated by v naught. So this is another way to find work that you should keep in mind, but it will probably also be on the formula sheet. It's just useful to understand that this is useful for problems where that's velocity is given, and the other one is useful for the majority of other problems.
But actually, it does on YouTube.
Are you serious?
What?
No, can you
That's
do
crazy.
this? Can I videotape
Why are you
it?
filming me?